Hi, everyone. Good afternoon, and thank you for being with us today. I'm Nisarg Shah. I'm an associate professor at U of T's Department of Computer Science and also a research lead at the Schwarzman Institute for Technology and Society. And I'm very excited to be moderating today's SRI seminar featuring my esteemed colleague, Adam Tauman Kalai. Before we begin today's session, I'd like to take a moment to acknowledge the land on which the University of Toronto operates. For thousands of years, Toronto has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. And today, this meeting place is still home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to live and work on this land. While some of us may be joining from different places today, we invite you to reflect on the history and relations of the land that you are on. All right, a few logistics before we begin. This session is being recorded. Our speaker will speak for about 50 minutes, followed by Q&A. He has invited questions throughout the presentation, but if there's something kind of very long-ended that you might want to ask yourself, then we would reserve it for the Q&A session afterwards. And then during that Q&A session, we would encourage you to raise your hand, use the raise hand function in the Zoom chat, Zoom meeting controls. And if you are in a place where you're unable to unmute, then you can just type your question in chat, and then I would be happy to ask them on behalf of you. Now, without further ado, let me introduce today's speaker, Adam Kalai. Adam is a research scientist at OpenAI, specializing in AI safety and ethics. Before joining OpenAI, he was a senior principal researcher at Microsoft Research New England. His expertise spans a range of fields, including algorithms, fairness, machine learning theory, game theory, and crowdsourcing. This is extremely diverse. Adam received his BA from Harvard and his PhD from Carnegie Mellon University, and he has served as an assistant professor at Georgia Tech and the Toyota Technological Institute in Chicago. He is also a member of the science team of Project SETI, an interdisciplinary initiative to understand the communication of sperm whales. His accolades include the Majuluk Prize, multiple Best Paper Awards, and NSF Career Award, and an Alfred P. Sloan Fellowship. We are very excited to have Adam with us today, and we look forward to his presentation on when calibration goes awry, hallucinations in language models.
It's an honor to be here, and I'm glad to get to know people at the SRI Institute. Today, I'm going to be talking about joint work with Santosh Vempala. It's coming up or it actually was presented in this most recent stock conference on the theory of computing. This was work done based on my time at Microsoft Research New England, but I continue to work on hallucination at OpenAI, and I feel that it's still relevant to that work. But it's mostly a theoretical understanding of hallucination. So I'll start with a fun example of writing an obituary for myself. You can ask ChatGPT or any language model to write an obituary, and it happily goes on and writes an obituary, and it says. Adam Kalai died away on April 1st, 2024. I thought that actually that date was pretty fun. That would be a great day to die, April 1st, because I just picture my wife telling all my friends, oh, Adam died on April Fool's Day. I don't know if you celebrate it in Canada too. But anyway, and nobody would believe her. So but anyway, it goes on and it talks about all kinds of random facts. It makes up that's not the name. My wife is not Rachel. I don't have kids named Samuel and Emily, and it gets full of details, as many of you have experienced, where the language model just seems to make them up out of thin air, which is not something that humans do very often. So it's kind of a mystery for many people about why this happens, and I would like to try to illuminate some of that with some analysis today. It's not just a fun curiosity; it's actually a major problem. Many people have been harmed by this, especially in legal or medical domains. If it hallucinates and gives you bad medical advice, it's really obviously a major problem that we're working to fight. So what is a hallucination, first of all? A hallucination is a plausible but false or misleading response generated by an AI system. It's already in the dictionary. This is the third definition of the word hallucination in the Merriam-Webster dictionary. So that just shows you what a big problem it is. but to really dive into it, let me just give a few examples of what's a hallucination and what you might or might not call a hallucination. And in this talk, actually, we'll distinguish those in our model. But you might say, well, okay, first of all, in the language models I'm talking about today, this is a classic language model which sort of completes a sentence or a document. You give it a prefix of text, and then it'll complete it. So if you say humans only use 10% of, then it might say, many of you have heard this, their brains. And I don't really consider that a hallucination. I mean, it's in the training data. That's a myth that's been perpetuated many times. And it's not exactly a mystery about why a language model might complete it that way. Similarly, if it does some calculation and it says John Doe was born in 1979 and died at 2025 at the age of, it should be 46, but it actually said, let's say it said 64. That's a miscalculation. That's not, I don't really think of that as a hallucination of the type we're talking about. And so we'll see why, how to distinguish that from the type of hallucination which we just saw, which is like a factoid, which is some, plausible, believable thing that just seems to come out of thin air. Why did the language model make up that, if we even just gave it the prompt fact and it just made up some detailed fact about some random person, which has nothing to do with reality, that is what I think of as a hallucination. Okay, so we call the set of plausible but facts, plausible things which could be facts but could also be hallucinations, factoids. Okay, so first let's talk about what is a language model and what is pre-training. And sorry, I should back up and say we don't really feel that language models must hallucinate. It's the calibrated language models must hallucinate. So we're hoping that language models won't hallucinate. They won't be calibrated as a result of our analysis, which is fine. But initially, when you pre-train a language model, usually it turns out to be pretty calibrated, as I'll talk about and define. So I'm kind of explaining why is this natural process of pre-training a language model to be accurate at predicting the next word, why does that lead to this hallucination in the first place? Okay, so a language model is a probability distribution over documents. And these documents are strings, and it assigns probabilities to each string. That's all it is a probability distribution. And you can think of us as having a distribution over documents. So the training documents are actually just samples from some ideal distribution over documents. And we have n samples, n may be very large. And there's some distribution, d, over documents. And these are n samples. And now it's not super important that you follow this part of the math, but in a classical maximum likelihood setting, you want to maximize the probability of the documents you've seen. So you choose the parameters of your language model, let's call them theta, to maximize the likelihood of the documents you've seen, which you can also write equivalently as maximizing the sum of the log likelihoods of the documents. Now, maximizing this exactly is not technically what you want to do. The parameters or the language model that would actually maximize the likelihood of the training documents is actually the language model which just assigns uniform probability to all training documents. So you can think of that as the stochastic parrot language model that assigns equal probability. What we really want, a language model that just outputs a random document from the training distribution. That's actually a pretty good language model in terms of hallucination, but it's not very good for anything else. It doesn't generalize. What we really want is a language model which on future examples drawn from the same probability distribution as the training distribution has pretty high probability. That's that's the goal of language modeling. And as I said before, in our examples, we think of the language model. If it's a probability distribution of our documents, you can use it like a good Bayesian to compute the probability of any completion given the prefix. And let me illustrate that with a simple example. And as I said, feel free to interrupt with any clarification questions. It'll be a much more fun talk if there's a little bit more dialogue. So okay, so how does language models work at the word by word level? If it's a distribution over documents, here's a distribution over 10 sentences. They're all true sentences. There's no need to hallucinate. And you can think of this as a word by word distribution because you can say, well, the probability of the first word is is 40%. Okay. And given that, let's say the first word is the second word is the word sun with probability half, and then the word rises with another probability half. So the probability of the sentence, the sun rises, is just the product of these probabilities, which is 10%. So this is fully equivalent. And my point here, which is an important one, I think, is that thinking of the distribution as a next word distribution or as a document distribution are completely mathematically equivalent. So somebody says, "Oh, the reason language models hallucinate is because they predict one word at a time." You can argue, at least I would argue, that that's not necessarily the most meaningful criticism, or at least you have to make it more precise, because I speak one word at a time. Anyone produces one word at a time. The fact that we generate things one word at a time is not an inherent, doesn't mean we think of them like one at a time, is not an inherent reason to hallucinate. So maximizing next word probabilities is fully equivalent to maximizing log likelihood of the entire documents. And again, the probability of any document is just the sum of the log probability of a document is the sum of the log probabilities of the individual words. In this talk, I'm going to ignore computational costs entirely. Things might be a bit different if you were talking about generating words one at a time and you worried about computational costs. But this whole talk is actually going to be just information theoretic. I'm going to show you why a language model would hallucinate even if there were no computational limitations. Okay, so feel free to ask any questions, as I said. Okay, so let's review some reasons why language models might hallucinate. Okay, and okay, so first, a commonly mentioned reason why language models might hallucinate is the following: they might have bad training data. Okay, and that makes a lot of sense, right? If you have bad training data and you train your language model full of mistakes, with false information, then you're going to generate false information. That's the classic garbage in, garbage out, fact from machine learning. But that's not the one we're going to focus on today. Another reason is that, language models, as we mentioned, have a prompt. And what if somebody gives a tricky prompt, which is very different from your training distribution? So, they say, "Oh, what were the 7 elves of Boston named?" or something. And there aren't 7 elves of Boston. So what do you expect it to do but hallucinate? And that could be another reason why language models hallucinate. But we'll argue today that they'll hallucinate even if the prompts are not tricky, even if they're simple prompts that are, all over your training data. And what we will argue is that hallucinations arise whenever you have a distribution of facts which is unlearnable, which might be heavy-tailed, which has sort of like a lot of arbitrary, hard-to-learn facts. And we'll get into the details of what that means. But the assumptions we're going to need, now at first these are going to sound strong, but I'm going to tell you why that's not the case. So first, let's assume that every training document contains one fact. So there's not noise. Is it gray area? Is it true or false? Let's just assume every document has one fact exactly. Okay, not 2 facts, not 3 facts. And everything is a fact or a hallucination. It's not tricky. In reality, it's a little vague what's true and what's not. And we're just assuming that the documents are independently distributed and not changing. There's a fixed distribution. Of course, the real world, there's there's news, and a lot of things change over time. But to make our analysis simple, we'll just assume everything is IID. And to avoid the case of tricky prompts, we're just going to assume that every single document starts with a word fact. And when we prompt the language model, we're going to prompt it with a word fact. So these sound like ridiculously strong assumptions, and they are, but they're very simple. And the point is that we're going to argue that language models will hallucinate even under these ideal settings. So even in an ideal world where each document has one fact and it's true and there's no noise in the training data and all that, the language models will hallucinate. So in a realistic setting where the training data contains errors and multiple facts per document and gray areas and the world is changing, you would sure expect the language model to hallucinate even more, right? I mean, if it hallucinates in an ideal world, it should hallucinate in the messy reality where things are not always true or false and you have noise in the training data and everything. So, but the surprising fact is that language models, the way they're trained is really to hallucinate even under these ideal conditions. Okay, so that's the point of all these assumptions.
Adam, there is a question on chat that I think
Yes.
would be useful to set the context right. So, Steve asks, are the language models incapable of saying I don't know? It seems that they answer
Oh,
any question whether or not they find relevant information, and I think that this kind of relates to your something like tricky prompt. Why is that even an issue? Like, why can't the language model just say I don't know?
excellent question. And thank you for bringing that up. So, of course, you're right that if a language model is never trained on data that says, I don't know, it can't generate, I don't know. So that's kind of one insight about why these language models might hallucinate, is that they may not be trained on that. But let's dive into what should happen statistically if we train them in this case. And if we assume though that everything has the prompt fact and all the documents start with the word fact, then at least it's not the case of tricky prompts. So they they're not forced to answer, right? But technically they're trained on training data, which has a bunch of answers that are all not, none of which are I don't know. So you're right, kind of you've got great intuition there that if you never saw I don't know in the training data, then you might not might not predict that that's what's coming next. And these language models are predictive models. Thank you for that question. Appreciate it. Okay, so let's dive into some of the analysis. So these factoids, they're arbitrary, plausible pieces of information, like, so and so died on some date. Or this paper was published on a certain date. We've all had the language models hallucinate on references. We would love it if they would write the related work section of our papers. Okay, so I'm gonna put you on the spot here and ask you to be a language model. And actually, I would love it if anyone wants to unmute and answer my question. So pretend to be a language model. It's actually a really tricky job. So here, let's say this is your training data. I've given you 10 facts or I'm sorry, you can't unmute, but I guess you can put it in the chat. So I'm asking you, to be a language model and think to yourself, if this was my training data and I saw all these random depressing facts about who died on what date, looks like there's many mentions of Alan Turing. So there's some celebrity here like Alan Turing, who died on June 7th, 1954. And then there's a lot of kind of nobodies like me who might, when we die, will be mentioned once in some obituary. Let's say that this was your training data, okay? And now the challenge to you is, and there's no really wrong answer here, but what would you, if you were a language model, what kind of probability distribution would you generate to model this data? And I'll pause for a second in case anyone has the answer they want to type into the chat. I haven't given this talk virtually. I've done it in person for a while. Often it takes a while for somebody to come up with an answer, but people always do. Okay, so I can see in the chat a bunch of good answers. So so a lot of people are saying they would put Alan Turing died on a certain date. Yeah, well, that makes a lot of sense. So yeah, so I'm going to summarize what I saw in the chat and say the following distribution, which I think is there's many answers, but one of them is the following: is half the time Alan Turing died on this specific date, which is right, and then half the time we're going to pick a random name and say they died on a random date. How exactly we write that distribution over strings and what distribution over dates, it's not important to this talk. Let's just say there's some distribution. So that's an okay language model. And it generates almost 50% hallucinations because half the time it generates some random name died on some random date, which is probably not very, very unlikely to be true. So this is not a great language model from the point of view of generating stuff. I mean, language models are randomized, I should have mentioned. We're talking about when you ask a language model something and you run it twice, it's called temperature one. When you run it, it generates different things. And so, this is a language model, it's randomized. In this particular language model, if you start with the word fact it's just going to generate half the time hallucinations. Now, this language model is calibrated, and we'll define calibrated in a second, but it's some weak notion of accuracy, which is not necessarily actually good for generation, but it's good for prediction. So this language model is actually not a bad predictive model if you're trying to guess what somebody was about to type. Yeah, the fact that they're typing a random name on a random date is actually not a bad prediction. But the fact that it hallucinates half the time is a very bad thing. Where does this half fraction come from? Well, if we change the training data and we tweaked, what fraction of these things are Alan Turing, then that would actually determine the rate of hallucination. So the rate of hallucinations is this like a preview to the technical result, is the fraction of facts that appear about half the time. Okay. Now, another language model, which I saw mentioned in the chat, that doesn't hallucinate is the stochastic parrot language model, which just picks a random fact from the training data. Okay, and that would be, so half the time it'll say Alan Turing died, and then 10% of the time it'll pick that random person, Max kind of thing. So this language model has some advantages. We call it the stochastic parrot language model in honor of that paper. But it never hallucinates, but it's also not very predictive. So it generates things it's not calibrated. Like it thinks Max Kenneth Fennell will be stated, Porter Max would be mentioned 10% of the time, whereas in reality, if you took future samples from this distribution, you'll never see Max, or extremely rarely would you see his name again. So that 10% is a way overestimate. And a language model like this, which just memorizes the training data, is not very useful. It doesn't hallucinate, but it doesn't. It's not useful in any other way for generation. Or you could take the language model, which generates only Alan Turing died on 100% of the time. And this is really the conundrum that the language model is facing in a very simplified setting. Maybe it realizes that these other facts are unlikely, and that the truth, what somebody's likely to say next is some random name died on a random date, but that's probably not true. So what distribution is ideal? And that's the problem that we have to solve in alignment. Really, is what do we want to say, given that we do not necessarily want to match this distribution or our best fit of the distribution, given that we can't. Okay, so here's a kind of a nice toy theoretical model which will help us understand what's going on in more detail. So there's a set of plausible factoids, which we call P, and those consist of facts, like the white things here, and then hallucinations, which are the red things. And there's many more hallucinations than facts. That's a fact of life, is that most things are not true. I could tell you all kinds of people who died on what date, or what people ate or did or said, or all kinds of facts about the world, which are plausible statements about the world, which just aren't true. And there's a lot more hallucinations than facts. That's an assumption we'll make. And then there's the training data, which is also much sparser than the number of facts, the green things. In the training data, those dots, you don't see all the facts in the world. If you did, you wouldn't need to hallucinate. If there weren't very many true facts in the world and your training data was big enough to cover every single fact many times over, you wouldn't need to hallucinate. But the reality is the training data is much smaller than the number of facts. Okay, so let's have a very simple warm-up model, which is kind of a toy model, where we assume that there's a uniformly random set of facts, which is drawn actually randomly from the set of factoids, some fixed size, and then everything else is a hallucination. Okay, so those white dots are randomly drawn, and then the green dots are uniformly randomly drawn from the white dots. So the true data distribution is uniform over these white dots. Let's call that D, and it's uniform over the facts. And then no matter what learning algorithm we're going to use, we can say the following statement, which is with high probability, 99%, the probability that if we learn a language model, let's call it D hat, the probability that a future fact from this language model is a hallucination, lies in that hallucination set, is going to be really high. It's going to be close to 1. It's going to be almost 100%. It's going to be 1 minus, now there's a few terms here that I'm not going to define, but I'll give some intuition about. The miscalibration rate. As I said, language models tend to be calibrated. Miscalibration is some very weak notion of accuracy or error. And so that, think of that as a very small number. So it's going to be 1 minus that. And then minus n is the number of training examples, and f is this, the denominator there is the number of facts. So n over f is a very small number because there's many fewer training examples than facts. Or if there aren't, if the number of training examples is bigger than the number of facts, then our bound doesn't say much. It just says the number of hallucinations could be 0, which is a reasonable bound. And then there's another term, which is 200 times the number of facts over the number of hallucinations. And again, we're assuming the number of facts is much smaller than the number of hallucinations. Or if most things in the world are true, then again, our bound won't be very meaningful. But typically that's an exponential. Both of those are exponentially small fractions. So any questions on this, feel free to chime in.
There's one question about how the factor of 200 comes from.
Right. Yeah, so the 200 comes from our analysis. I'm not going to guarantee that it's the tightest number in the world. It's related to that probability 99%. If I made it 99, 95%, it'd probably be more like 40. Yeah, so this is a lower bound, a theoretical lower bound. And again, it might not be the tightest possible, but it conveys a lot of the intuition. But I think that ratio is so tiny, the number of facts, the number of hallucinations, that 200 is not even that big a number when you multiply them. Good question. Thank you. And feel free to interact with others. So, okay. So let's talk about calibration for a second. What is this miscalibration term? So calibration is an old idea that goes back to a philosopher named Dawud, who says, a simple example, like on days when the weather forecaster predicts rain at 20% chance, it rains 20% of the time. Okay. And so that's kind of a simple idea. And it's not about accuracy now. If let's say that on average over the year, it rained 20% of the time, then actually you could be calibrated really easily just by always predicting 20% chance of rain, regardless of any other facts. And you would be calibrated on days where you predicted 20%, it rains 20% of the time. So you don't have to be a genius to be calibrated. It's kind of really easy to be calibrated. As long as you get your probabilities right. You wouldn't be calibrated if you said 90% chance of rain all the time and it only rained 20% of the time. But then you should realize that and adjust your 90% down to 20%. Of course, you could also be calibrated by perfectly predicting, 100% chance of rain on the days when it rains and 0% chance of rain on the days where it doesn't rain. Then you're also calibrated because on the days where you predict 100% chance of rain, it rained. And on the days where you predict 0% chance of rain, it didn't. What you don't want to do is predict overconfidently, let's say 100% chance of rain, and then it turns out that it doesn't rain all 100% of the time. Okay. Now we're going to need to change that definition a little bit for facts, because we're not predicting like a binary classifier of is it raining or not. We're just predicting, which fact is going to appear or which factoids are going to appear. So the language model, assigns probabilities. Again, we're assuming every document has one factoid. So we're saying the language model, generates factoids with some probabilities. And what we're going to say is among factoids that it generates with some probability p for any positive number p, or even 0, on average, those factoids should occur with the same probability, roughly, p in the true distribution. Remember, there's some true distribution d. I apologize. I think before I called this language model distribution d hat, but now I'm calling it p in this slide. So if the language model is a distribution, p with some hyperparameters theta over factoids, and the true factoid distribution, true fact distribution is d, then it's going to be calibrated if for every probability p within the range of 0, 1, on average, facts drawn from your distribution that have the right probability. P is the average probability according to the true distribution d of those facts p. And so this is a condition called calibration. And the reason it's not exactly easy to achieve, but if you're off, if you're miscalibrated, all you have to do, you don't have to change all your predictions and everything. You can just apply this post-processing step where you change your probabilities and say, oh, that probability I said before, I know I said it was 20%, but actually now it's more like much lower. It's 10%. Okay. You just adjust on a probability by probability basis, not on a document by document or fact by fact basis. And then, of course, this whole thing can be, you don't have to be exactly right on every probability. There's some, tolerance epsilon that's a bit messy to deal with, but it's always added to these things. Okay. And let me actually jump ahead a second and show you that the curves that we have. Actually, before I joined OpenAI, they published a tech report about calibration, showing that the language models, when you pre-train them to maximize the likelihood of next words, oftentimes they're very, very calibrated. This is not exactly the same definition of calibration, but it's a well-known fact that language models are encouraged to be calibrated. As I said, if they're not calibrated, then actually adjusting them, post-calibrating them, if they could adjust their probabilities to be calibrated, that would reduce the pre-training loss. It would increase the likelihood of documents, you can argue mathematically. So that's kind of the reason that maximizing likelihood of training documents leads to calibration. There's a good justification for that. Okay, so that's the just explanation of this miscalibration term. All right, so now let's feel free again to interrupt with any questions. But if there are none, let me go to some more interesting cases. One is the not uniform case. So again, we're still gonna, what does it mean? It's symmetric, but not uniform. So think about the Alan Turing case. There's a celebrity, so it's not a symmetric distribution, it's not a uniform distribution, but let's assume that it's symmetric. So there's some real world, and the world, there were some random celebrities and their death dates are random. Their names are kind of random-ish and their death dates are random. But then the distribution may be highly non-uniform. Maybe there's half the time it's on Turing, or there might be some heavy tail distribution or whatever. But there's some distribution, which is D again, the data distribution over facts, which is not uniform, but it is symmetric. The prior over which facts are true is symmetric, and their distribution is symmetric. Okay, so in that case, we're going to have now, again, D hat is our language model, and this is just another way to write the probability of us outputting a hallucination with high probability. Before we had 99%, now we have 1 minus delta for any small number delta. Our probability of hallucinating, here's a really interesting interpretation here. RF is the rare fact rate. It's the fraction of facts that appear just once in the training data. That appear exactly once, not twice, not 0 times, but exactly once. And those are very suspicious, because things that appear just once, as I'll argue in a second, those tell you about the facts that you're not seeing and the facts that you might be tempted to predict, which may or may not be true. Then there's a bunch of other terms similar to before. There's the miscalibration rate. There's some other term here, which again depends on the ratio of facts to hallucinations. Again, that's an exponentially small ratio, so that you can kind of ignore the 3 over delta. But if delta was 1% like before, that would be 300. And then there's a final term now, which depends, note the denominator there is the number of training example, which could be, millions or billions. So a very small number. So now we're not saying you're going to hallucinate most of the time, like with Alan Turing. If that's half the time in the data, then your distribution will be half the time generating Alan Turing. You're only hallucinating half of the time. But this is really that bound I mentioned, where we're saying the fraction of hallucinations is roughly the fraction of facts that appear exactly once in the training data. Okay, that's kind of a neat and simple interpretation. Again, the miscalibration rate is typically small, but this rare fact rate is some number between 0 and 1, and actually depends on the particular domain. And where does that come from, that number between 0 and 1? It comes from this beautiful Good-Turing estimator due to Alan Turing of the missing mass. And so what Alan Turing said is, any distribution over any set S, you have some set, you draw some, you go fishing. And let's say, you catch 100 fish. And then you want to know, okay, what are the chances that if I were to catch another fish, I would be one of the same kind that I've seen? Maybe you caught, 50 redfish or 50 salmon, and then 50 other unique kinds of fish, each one just once. Then you say to yourself, what's the chance that the next fish is going to be a different one? Well, that's actually pretty high. You'd say it's about half, because you'd say, look, half the fish were these weird, unique varieties, and half the fish were salmon. Okay, so the salmon I know half the time. The other stuff, I only saw them once. I don't really think I'll see them again. I'll probably see something actually new with the same rate. So that's kind of the elegant estimator. It's different than twice. I mean, if you did this experiment, you got 200 fish and you got 100 salmon, and then 100 of them that, 50 of them that appeared twice. So you saw them each twice. Then you say to yourself, oh, no, no, no. Those things that appear twice, those are not once in a million, once in a billion kind of things. Those are likely things. I saw them twice. I have already kind of a half decent estimate of the chance that they'll appear again. There's a big difference between once and twice. Okay, let's see. So I also noticed in the chat that somebody was asking this question about the number of hallucinations. Somebody asked in the chat about the number of hallucinations. And the size of this set H is, the number of possible hallucinations in the case of death dates or deaths. It's the number of names and dates, which is, huge, as you would point out. And the number of true facts is the number of people who actually existed and died on a certain date, which is way smaller. Okay. So good question. Thank you. All right. So that's the Good-Turing estimator. And now I want to mention something that's not in our paper. It's a new result that we're planning to add and publish soon. And it takes it one step further. So these kind of were toy models where we were assuming that the facts are independent, which is a very strong assumption. I mean, like things, in some cases, facts are independent, like death dates, but in some cases, they're really not independent. And so when do we expect hallucination on, the complicated facts that we have in the world? And so here we're going to compare, we're going to try to leverage some intuition that you might have from classification. So binary classification, we're trying to learn, is something true or false, right? Or is something, cat or dog, or whatever you're trying to learn. And, there's been a long history of learning theory and statistics, machine learning on this classification task. This unsupervised learning is a bit new. It's always been there, but it's less discussed. It's only been popularized recently. So in classification, we all know, so there's some things that are easy to learn and some things that are hard to learn. And so, for example, remember the arithmetic facts we brought up earlier. In arithmetic facts, you can learn them. I mean, if you're smart enough, you can see those training data and say, oh, you can learn even to generalize and learn from small examples to big examples. You can learn a lot. So, in the case where there's a systematic set of rules and you can learn it, we actually don't think you need to hallucinate. Okay. If you can get high accuracy classification, then we don't believe there's a good reason to hallucinate. On the other hand, if it's really hard to learn, like it's really hard to learn to generalize these hallucination facts. Excuse me. Sorry. It's really hard, not hallucination facts, but the facts about obituaries, about who died when. I give you a bunch of facts in the training data. You can't learn that. It's a very hard distribution to get high accuracy on. So we're going to leverage that intuition about what you can classify accurately to help understand where you should hallucinate and where you shouldn't. Now, this is a bit of a complicated theorem, but it's what it's saying is that you can view it two ways. One is you can say if you're not hallucinating, then you should be able to classify very accurately. Or conversely, if you can't classify accurately, you're going to have to hallucinate or be miscalibrated. So the theorem says if you're rarely hallucinating, if you're only hallucinating epsilon fraction of the time and you've got a calibrated language model, then you can actually distinguish the true distribution. So if you now consider a binary classification problem where there's some distribution D, it's actually got to have positives and negatives. So the positives are according to the true world distribution over facts, and the negatives are uniform, let's say, over the hallucinations. Okay, and our job is to distinguish. You've got 50-50, that somebody flips a coin and gives you either a random fact from the world or a random hallucination. As long as there's, let's say, more hallucinations than facts, then if you're rarely hallucinating, you're going to be 99 or almost perfectly accurate. That's what this 1 minus 3 root epsilon means. Okay, so we're trying to learn a classifier. And what is our classifier, actually? We're just going to use the language model itself. So our classifier, the true classifier is, the true function we're trying to classify is this function f, which is 1 if it's, let's say, positive 1 if it's a fact, negative 1 if it's a hallucination. And our classifier is going to predict, let's say, and sorry, the distribution. In order to define a classification task, as I said, we have to have a classifier, a true classifier, which is F. We need to define a distribution over data, which is going to be half the time true facts, D, and half the time hallucinations, random hallucinations, okay? And our predictor, we're going to use the language model. We're just going to say, look, if the language model assigns probability bigger than some threshold theta, we'll call it a fact. If it assigns probability less than the threshold theta, and that theta depends on epsilon and the number of facts, then we're going to call it a hallucination. And that is going to turn out to be a pretty decent classifier. Okay, so the intuition is it's easier to classify. It should be easier to classify than to do language modeling without hallucinations. Why? Because in classification, you actually have labels and you have examples of positives and negative examples. You have examples of hallucinations of things which are not true. When you're doing classification, when you're doing language model learning, you only have positive examples. You have no examples of hallucination in your training data, hopefully. So now you're effectively forced to internally learn a classifier, which is what is true, and distinguish what is true from what is false, without any examples of negatives. That's harder. So if you can learn to classify, to generate things accurately without hallucinations in the language model setting where you only have positives, of course it makes sense that you should be able to use that as a classifier to distinguish true things from false things, because it's not generating false things. Okay. And as I said, conversely, you can turn this bound around and you say, if you have a hard setting where you can only, 50%, or there's some rate at which you cannot accurately distinguish facts from hallucinations, then you're going to hallucinate a lot. The language model, a calibrated language model, is going to hallucinate at some high rate as well. And so this bound relates to these two things. Okay. All right. So, okay. So somebody asked an interesting question, which is if we keep all other simple assumptions and allow different training samples to be about the same fact. Oh, yeah. So that's a tricky case. So what somebody's asking about, what if different training examples represent the same fact? And yes, in the real world, there's going to be multiple ways to write the same fact. Now, I leave it up to your intuition to think about whether that's going to make our life easier or harder. In this ideal world where there's only one way to write a fact, we're arguing you need to hallucinate. In the real world where there's 10 different ways or a million different ways to write the same fact, do we think that hallucination is going to get easier or harder? I personally think that it's going to get harder. But our math is only about the simple case where there's one way to write every fact. We actually cover a little bit more general cases in the paper, but I'll leave that to the paper if you're interested. Okay, so as we talked about, this pre-training leads to calibration, but we're going to get into the, why we shouldn't be depressed, and hopefully, we can solve this problem. So the statistical interpretation is that, as we said, the hallucination rate, if you just try to maximize your next word likelihood, which is called pre-training, should be at least the rare fact rate minus epsilon. Okay. So it makes you think, what fraction of facts would appear just one time in the training data? So country capitals, it's not going to hallucinate on those. Those appear many times in the training data. Try to get it to say, what country has the capital, and make up some random capital or something. And it just won't hallucinate. It's quite challenging to get hallucination out of some very common fact like country capital. Now, here's the most interesting interpretation, in my opinion, from our paper, is that something like books and article titles, which literally make up the title of a book. Now, I mean, come on, books are all over the place. I mean, if you see something, if somebody tries to publish a book or even a research paper, even my papers, which have, only one citation or 0 citations, you better believe I put them on my webpage. They're on archive, they're on whatever, all the mirrors of archive, and I put them everywhere I can, because, the point of publishing an article or a book is to get attention. So I claim that these books and articles, most of them appear many times in the training data. And so mysteriously, our bound should say you don't need to hallucinate on these. And yet in real life, language models hallucinate on these, unfortunately, still like crazy. We're working on trying to reduce that, but they do. I apologize. Um, and so, why is that? Well, remember that our bound is a lower bound. It says, that you must hallucinate at a minimum at a certain rate, and our minimum rate is quite low. And actually, I don't think mathematically, statistically, you need to hallucinate on these things. Just a very simple, reality is that a lot of language models were moving in this direction of retrieval, where they search the web. And that's the right thing to do on a case where there's a large data set of things which you don't want to store in the weights of your language model. What happens is the language model is a bounded capacity thing. There are so many facts in the world, not just books and article titles, that they can't all be memorized by the language model in its inside. And so it's probably, some other limitation which is not covered in our analysis. It'd be very interesting to generalize our analysis to some kind of thing. But remember that our learning intuition does carry over. So maybe a classifier which is trained, with a neural network, like to try to distinguish these things is not, or at least our language models are not good distinguishers of books from, fake books. Let's put it that way. Okay. And then death dates, something like that. Our theory would say, yeah, well, there's a heavy tail. It's a very hard distribution to learn. There's a lot of things appearing just once. We do expect a high hallucination rate in those. Okay. Okay, so what about adding new facts to the training data? Maybe a good solution, if you don't have, if you're hallucinating a lot, maybe you should add more death dates. And it's kind of interesting to think about that. But actually, when you think about that, the language model is doing its statistics. So it says to itself all of a sudden, oh, I see even more things appearing just once. We go to the Social Security Administration, you get all these death dates and you add them to your training data. The language model, you're actually teaching it to hallucinate. You're saying, oh yeah, this distribution you're trying to predict, it's full of things that appear just once. So when you generate stuff, you probably should generate things that you haven't seen before. Okay. Uh, what about if you run over your training data many times? That's kind of an intuitive idea. Or you can think of it as resample from that, or it's called number of epochs. And essentially, that actually might help with reducing hallucinations, because now your language model is seeing these things many times, and it's if it's doing its job as a statistician, it's saying, oh, there aren't that many real facts in the world. There's a small set of facts. I think most of them are covered in my training data. There's a lot of them, but most of them are appearing many times. I'm going to try to memorize as many as I can. No need for me to start generating masses of facts that I've never seen before. So it couldn't reduce hallucination. Unfortunately, it can also increase regurgitation. Remember, the stochastic parrot language model just generates a random fact from its training data, just reproduces a training document, never hallucinates. Unfortunately, not useful language model, and it regurgitates like crazy. So there's this interesting trade-off. And now what I want to shift to talk about very briefly is how post-training must teach the language models to say, I don't know. That's what we have. We have, let's say, very little of that or not enough of that in the training data. And so post-training can reduce hallucination and increase miscalibration. This term post-training is a funny term. I mean, both pre-training and post-training are actually training the model. But post-training just means it happens after that pre-training phase, which is where we're trying to maximize the likelihood of the next word. Post-training involves reinforcement learning from human feedback, a bunch of really cool techniques that I'm not going to get into. And again, post-training can help a lot. And it turns out, if you look at this GPT-4 technical report from last year, they show that the post-training, unfortunately, after post-training, the calibration goes way down. But it's actually a fortunate thing because you don't want a calibrated model, because calibrated models do hallucinate. And so post-trained models hallucinate less than the pre-trained models. So we're working on that. That's what our post-training does, and tries to reduce the calibration, well, tries to reduce the hallucination, and as a byproduct, also reduces calibration. But both hallucination and calibration. Okay, another way to get some intuition here is, again, I think of these language models more, the pre-training stages, more predictive stages, predicting what you're typing, like a phone keyboard. Remember those phone keyboards, they predict what you're going to type next. It's helping you. So if you say Adam Kalai died on your phone keyboard, it has a prediction, and you could just tap away and you can say, oh, I can't, and it'll predict. And these are actually okay predictions. I mean, if you think about it, um, you know, they're all fine predictions, and we don't even think of it as a hallucination. But somehow, because we repackaged these predictive language models as a generative model, all of a sudden it's mysterious why they're hallucinating. But nobody was surprised when our phone keyboards generate gibberish. But actually, they're trained in exactly the same way. So I would argue that's really the surprise is that the language models do so well at generation that we're kind of tricked in this way. So in my last slide, in the human brain, there's two kind of language models, two areas of language models. One is in the back near the ear. I mean, this is a bit of a simplification, let me say, but it's consistent. And so this part near the ear is the listening language model, okay? And that's, expecting to hear a bunch of stuff, and it needs to be able to, parse what it's hearing, and it'll say some things which it knows, but it'll also hear a bunch of random facts. I mean, we hear a lot of things. We hear children talking. It doesn't mean we talk like children, right? So we need to be prepared to hear children and people with all kinds of accents and differences from us. And that's the listening language model. And then in the front end, if you generate from this language model, there's actually a condition called Wernicke's aphasia, where people kind of babble in a way which is not that different from hallucinations. And in the front of your language brain, there's an area closer to the mouth called Broca's area, which is another language model, which is responsible for production, not comprehension. And that's what you want to say. And that's different. As I said, you hear what children say, but you speak in a way which is different. You might hear some curse words and things. You don't want to speak necessarily in that same way. And the miracle of language models is actually that these initial language models, which were pre-trained as language models, are almost useful straight out, are very similar to the ones with appropriate prompting for generative models. And then there's all this RLHF and more work to be done in this post-training stage to make them really say what we want them to say. And as I alluded to in the talk, the main question is, what is it that we want them to say? We need to figure that out. And that's a super interesting question that I'm also passionate about and I'm very interested in, people are working hard on, is what is it that we want the language model to say, given that we don't necessarily just want to match the training distribution. We want to be smarter, we want to be better, nicer, kinder than our training distribution. What I want to say is thank you very much for the questions and inviting me. It's been a pleasure talking today, and I'm happy to take any more questions.
Thank you, Adam. That was such a fascinating talk. And now we are happy to move into our discussion period, and we welcome questions from all our audience. There are already a few questions on chat, but I'm sure that there will be many more questions. Just a reminder, if you'd like to ask a question, then please use the raised hand function on Zoom. And when it's your turn, our team will call upon you and request you to unmute and then ask the question yourself. And we also encourage you to really turn on your camera to ask the question. And if you're in a space where you are unable to unmute and ask the question yourself, then please feel free to continue writing the questions on chat, and then I'll be happy to ask them to Adam on behalf of you. Right, so I have a question there from Mitchell. Mitchell, do you want to unmute and ask the question?
Hi, yeah, thanks for this talk. Super interesting. I was wondering if you could expand a little bit more on the different levers that you have to solve this problem, insofar as it is in fact a problem. I mean, it is a problem, but I think like there's an interesting trade-off between an information retrieval, like as a search from with a pre-trained model, and prediction, right? And so maybe we don't want to solve this problem if we want to have a good prediction model. I guess my question is of the different levers you have. So data augmentation through like synthetic data creation was talked about in the chat. Then you mentioned instruction tuning with like reinforcement learning with human feedback. And then stuff like decoding, constraining the decoding with something like top P or something like that. And then, you mentioned careful prompting as well, either telling it, do not hallucinate, or maybe trying to do a bit of retrieval augmentation, or, or even steering vectors, right? They're the new thing that's happening right now, Golden Gate Claude and so on. Um, how do you figure out which of these knobs to twist? Because it seems that there's a lot of different knobs, and at least in my own work, it's really not clear to me which of these knobs to turn and when to try to solve these problems.
Great question. Yeah, so everyone has their favorite techniques. My personal view is that statistically speaking, maybe this RLHF is enough. So what I mean is this, what you'll do, what we do and many other people do, is you take a language model. You start with a raw language model that's been trained on just kind of predict the next word. I agree, predictive models are good, and there's cases where you want prediction. But the reality is most people want to talk to these language models, and so they want correct, authoritative answers, not just predictive answers. Hallucinations are really a major problem for many of us. So we want facts and correctness from these things. So what happens? Let's think about what happens if you do what I was referring to. So this post-training, classic post-training method called reinforcement learning from human feedback. So you can take a simple version is you just take the question that was asked to the language model, and you generate multiple, let's say 2 answers, and then you show it to human. You say which one of these is better. Okay. And now let's consider the case where one of them is correct and one of them is incorrect. Well, that's actually an easy case. And if the language model knows the truth, then, in any case, hopefully the humans will prefer the correct answer. And then let's consider the case where there's 2 generations. One is wrong, and one of them is I don't know, right? So if you can somehow, get your language model started to say I don't know occasionally, if your raters are doing a good job, they should prefer the answer that says, I don't know. And that's really the key moment where we can teach these language models to say, I don't know. And that it's a very simple method. Statistically speaking, I think that has all the juice you need to teach the language model, hey, we're no longer in this predictive game. Your now job is to optimize for these human raters, and the human raters always, if they always preferred, I don't know, to incorrect statements, hallucinations, then we'd be good. Now, the main problem, which is kind of a silly one, but is that human raters and humans in general, not just raters, but if you were just ask people, you show them responses, it's a fact of humans that they often prefer the confident incorrect answer to the statement I don't know. And so that's what's causing a lot of the problems, in my opinion. Behind the scenes is that this methodology makes sense and everything is good, but then these people are saying, oh yeah, this thing which sounds so confident and gives me a 10-point answer and gives me 5 article titles and stuff. Either they don't take the time they need to go check that those are hallucinations, or they don't have, in many domains, they don't have the expertise to determine that's hallucination, or they may literally prefer something which is or maybe it's got some hallucination in it, but a lot of good stuff, and they prefer the answer that's authoritative sounding and doesn't say I don't know. So in my opinion, that's kind of the lever that I'm most excited about, and the cause for the problems that we're seeing.
All right, thank you so much. Steve has a question. You also had a questions on chat, Steve. So you can
and I kind of you and I had a little bit of a chat, and I kind of want to get to that, but I want to just make a point that I'm not sure everybody knows of, which is the following: humans make hallucinations, and I don't mean that as in they're on LSD and they're having hallucinations. There's something, for example, called the false memory phenomenon, false memory effect, that if you show people a bunch of words related to the word sleep, so bed, sheet, tired, pillow, etc., and then a little while later you say, hey, we're going to test your memory for what I just showed you, and if you show them the word sleep, they will false alarm very high. They'll say, yep, that was on the list. And if you ask them their confidence, they'll be very high confident because everything that was on the list was related to sleep. And so it kind of feels like sleep should have been there, sleep fit. And that's what our brain seems to detect. Yeah, that seems to fit. And we do that. And so that was sometimes my referent when I come into LLMs and I think about what are their hallucinations, because I've certainly seen when I ask it for help with papers and I say, can you tell me some of the stuff that's in the literature around this phenomenon and kind of give me the story of, why is standardized testing supposed to enhance equality of education or something? It'll tell a story. It'll create hallucinations. It'll talk about studies that don't exist. But when you get down to it, it feels like that study should have been done. And if you do it, you'll probably find what it thinks. So that is, it's not just making stuff up out of nowhere. It kind of knows how all of the data fits together. And if you ask it about some middle point, it's not just a random hallucination. It's something constructed from the information it has. And it's not there. That paper doesn't exist, but it is more sensical than a word like hallucination might imply. So with all that said, all that just to say, do we want to get rid of hallucinations, or is this part of how we do things too? And is it maybe more a question of being able to detect the hallucinations? And so that's where we were having a little bit of a chat. We're saying, is there any other thing that could come out of this model that could be used? And as one example, we're playing with conversational bots, trying to create one that you can have a good conversation with. Every now and then there's lags. Some of that lag might be the text to speech and stuff like that. But is there any lag that's predictive from the model? And we also we talked about the notion in the chat that maybe it's just the probability. Could you just assume that something that's a high probability response is like high confidence, a low probability response is low, and we need the models to reflect that, to stop being so damn confident all the time, to start using words like I think, or it could be, or it seems reasonable that. And is there any information like that? And does speed matter at all? Is there a notion that the speed with which the LLM can deliver a response is indicative at all about something that could be confidence, or is that just forget about speed? All we have is probability.
A great question. So there's many questions there. First of all, I agree with you that the word hallucination is problematic. I think somebody mentioned confabulate in the dialogue. It is, there's other words, and maybe part of the problem is just the word that we use for it. I also agree that that the language model can be used to sort of detect its own hallucinations, and there's a number of papers on that, ranging from the simplest, which is you just ask the language model, hey, that thing you just said, how confident are you that it's true? And it's a pretty good classifier of whether or not it's true or not. Probabilities are okay. They're not ideal because certain facts have many different ways of writing them. So like a long sentence is just going to have a lower probability typically than a short. So it's not perfect. And then there's also, people train classifiers using the activations of the language model to try to look in the brain and see whether it knows whether or not it's hallucinating. But by and large, like there's so much overwhelming evidence that the language models do know it's encoded in their representations in various ways, whether or not they're hallucinating. I wrote a paper where what we did is we took all these references and we did this trickier way where we said, here's a paper title you just said exists. And in a separate session, we said, without showing it what it said, we said, who are the authors of this paper that you said exists? And then we do that 3 times, get 3 totally different answers. We know that the language model does not know about that paper confidently. So that's just an example of a way of testing it. Speed, or likelihood is another. I mean, I'm sure there's ways of getting some mileage out of that too. So there's a bunch of different techniques.
So you said something, I'm just curious, I'll just follow up with this last one. You're starting to give me the image that maybe we view what we're playing with right now as the engine, the core engine that drives a draft response, let's say, or something like that, but that we need other architecture around this to now evaluate that response, assess its confidence, and decide how it's communicated or something. Like could we all be trying to make the LLM deliver something perfect when maybe it shouldn't be what we want? Maybe it should just be starting the process and other things there to clean it up before its output.
Right. That's a good question. don't have a great answer for that.
Cool. Thank you.
Yeah, so many things here are so open-ended. All right, so there is another question from Silvio. Silvio, would you be able to unmute and ask the question?
Hi. Yeah. Thanks, Adam. Really cool talk because it gave me a new perspective on. Sorry, my video is just turning on. Gave me a really cool perspective on hallucinations. I never really thought about them as occurring that commonly for in distribution prompts. Like just the fact colon, which was your entire training data. You showed the hallucination happens then whenever the language model is calibrated. I actually thought of hallucinations as mostly occurring for out of distribution prompts, like Adam Kalai died, which never occurred once. And then, of course, it seems almost natural to hallucinate. So I was wondering if your analysis applies at all to the out of distribution case, or how you understand the relationship there.
Right. I mean, there's a lot of things which might appear to be out of distribution because you've never seen anything exactly like that before, may still be in distribution in the sense that, people are wacky and creative. And so there's the real distribution over what's in the training data and what people will type is very broad. So, but I do think that distinction between in distribution and out of distribution is worth making. And just my intuition is that, out of distribution is only trickier, right, than in distribution, because now you're challenged with, dealing with the out of distribution nature. But, it's not always trickier. I mean, like, if you take two well understood theories, math, some aspect, like the classic examples they always started with, write a poem about the prime number theorem or something. And that was their example of an out of distribution prompt because they believed that nobody had ever asked that question before or something like that, maybe. But, the language models did really well at that type of task, which involved two sort of systematic sets of rules, right? One is, the rules of poetry, what has to rhyme, and the other is the rules of math, which is what is a correct theorem. And language models, especially the big ones of today, they're going to cream that kind of question and not hallucinate. So I think it's, depending on how you define in distribution and out of distribution, I think it's really, a lot of it is this question of, knowledge and what's covered and what's not, what's learnable and what's not. But I do believe that the in and out of distribution hallucinations, we can, make progress on in the same way that every human, as it's kind of like, I think Steve was saying, every human is a language model. Essentially, we all speak and have produce in a generative sense, and we don't really hallucinate I mean, occasionally people hallucinate. What mystifies people is the ways in which language models hallucinate, which are really non-human-like or much more than humans. And so I think we can reach a point where we don't hallucinate, even in the out of distribution case. At a minimum, we can always say, I don't know. So it's really just, we need to learn the context in which it's appropriate to be creative and give us this, fiction, and the ones where we don't. But I don't have a theory. It'd be really interesting to have a theory if there was a way to generalize our theory. It's a nice idea to an out of distribution setting. I don't see an immediate way to do that, but it's a really interesting question. I mean, anything that sort of trivially takes the distribution, a hard unlearnable, requires the use of some unlearnable distribution, you would think would similarly face those problems, but it'd be very interesting to try to model that. Great question.
Thanks, Adam. There's another question by Joseph in chat who is unable to unmute. So I'll read out the question on his behalf. And I actually had the same question during your talk, which is this taxonomy of myth, miscalculation versus hallucination is very interesting. And it seems that these categories are dependent on the truth conditions in our society, which are kind of somewhat imposed outside of the LLM's knowledge, and the kind of it's even guided perhaps by a social process, which is not necessarily a statistical one. And so one way of thinking about this is that for LLMs, everything is a hallucination. It has no sense of the truth or false because it has no reference in the real world. And I also it makes me think of this data gemma that Google just pushed out of an LLM that is grounded in truth by connecting to the data commons repository of truths, established truths in the world. And I wonder if some kind of a combined approach like that could be helpful, could be the way forward.
Very interesting. Yeah, so that's a great question. So it's true that the set of truths is not agreed upon, and different people will have different views. I think there's a perception that language models are only trained on just random junk from the web, which is that's how early language models might have been trained, and but the data that goes into them is heavily curated. So we do have that opportunity to choose what goes in, what doesn't. Some of the data might be synthetic, so then we can generate things. I personally am not one to believe that you need embodiment or groundedness or anything like that. I think there's some beautiful papers which have shown that a language model trained on millions of games of Othello, let's say, have a beautiful internal representation of Othello, even though they were just watching people play Othello, but they can understand the positions. They can talk about hypothetical moves that could on a board that could never arise in real life. So I think I don't personally think they need to be trained on a weird some grounded or some distribution that's tied to reality in any way, which is kind of amazing, right? Because it's like a person learning, to speak without ever being connected to the real world. You might be missing a sense, you might be deaf, but you can still touch things, or if you're blind, you can still hear. So every person has multiple modalities. But what the language models have shown is that it's possible to learn just from one. But I don't see that as, in any way statistically impossible. I mean, there's a set of rules governing the world. If in order to learn to predict well, you have to learn those set of rules in as concise a way as possible, then I think that's a good way to do it. But I think there's a lot of room to play with what we do put into the language models. But still, what this talk shows is that, just putting a bunch of facts in there does not solve the hallucination problem. You need to do a little bit more.
Right, definitely. There's a hand raised by Ariel G. Would you like to ask your question?
Yeah, so I put it in the chat as well. I'm curious if you have takes on the recent 01 release, where it seems to have more hallucinations or as many as the previous version.
Yeah, I mean, if you look in the, there's a 01 system card that, that OpenAI puts out, and there's a section in there on hallucinations. And, if you actually look, the hallucination rates are actually lower according to that analysis. But let me comment on your feeling, which I agree with, in the sense that I think there's another phenomenon at play here. My personal opinion is that as a model gets better in other ways, the sense in which something the hallucination problem grows, if it let's say doesn't get much better at hallucinations but gets better at almost everything else, then the hallucinations becomes that really persnickety problem that really aggravates you, right? Like before, let's say it made all kinds of miscalculations and reasoning errors and all kinds of things, and hallucinations were one of the many problems it had. And now it's getting better in many, many ways, but it still has problems. Hallucination has not been solved. Then the degree to which the hallucination problem is bothersome and apparent, obvious, may actually increase.
All right. Next up, we have Sheila. Sheila, would you be able to?
Yeah. Hi, Adam. Thanks for the great talk. Nice to see you.
Nice to
I wanted to ask you about the distinction between syntax and semantics, and between manipulating strings as words versus really understanding their meaning, both in terms of the phrasing of facts in very different ways, but also in terms of, I don't know, referring to Alan Turing not as Alan Turing, but as the guy who cracked the Enigma code, and how we can get from where we are now, which is somewhat syntactic, although it does do a lot of, sort of reasoning, or seems to do some sort of reasoning by virtue of the way that it works, to really a form of semantics, which I think is that we understand that we can express some idea in many different ways, and we still want to be able to stitch those things together.
It's a great question. I mean, it's kind of remarkable that these entirely syntactic entities do such good reasoning, right, at the semantic level. Or maybe it's frustrating in some ways for some people, but I don't have a good answer of how that. Do you have any ideas of how to go? I mean, in our analysis, we kind of we gloss over that issue by saying, well, let's just think of, if in our paper, we actually say, okay, yeah, there can be many ways to write the facts, but let's assume we're calibrated on a semantic level. And so we have a semantic notion of calibration, which is that the probability we assign to any fact, its semantic version, is calibrated, right? Because calibration on a word by word level is not necessarily that meaningful or useful. So we do deal with that in the paper in that way, but I don't have a good answer. Do you have a good idea of how we should shift to the semantic level?
I guess so I distinguish between two things. I guess, to a certain extent, through cosine distance, in some ways we understand we have a distance measure for the relationship between things, and that perhaps is part of the clue. But they're also, I think about logic, for example, as one form of inference, they're the connectives, and an or and not that have particular meaning, and that really, when they're composed together to do inference or to understand semantics, it can really flip something from being, well, true to false, or yes to no, and that's quite profound. And so I think, yeah, I feel like there's more work to do in that area, and it may not be exactly along the trajectory that we're seeing right now, but it is, as you said, and I think too, remarkable just how much we can do with probability distribution and these autoaggressive models. Is pretty amazing.
That's a good point about the embeddings. Yeah, they do capture a semantic distance.
Yeah.
Thank you.
Thank you, Sheila. So next up, there is a question from Nicole on chat, but she's unable to unmute and has asked me to read out her question. So she's kind of thinking about digging deeper into where this kind of hallucination comes from. And she's asking if prompt engineering would be a good approach to find out how ChatGPT came up with the responses. And by observing the logics behind these responses, whether we can get some insight into the process that it took to generate these responses, and if this can even be pushed further to make some statistical analysis kind of from this prompt engineering approach.
So I see. So you trying to understand what the prompt engineering approach to hallucinations is. I mean, you can ask the language model, where did you get that idea from? And you can try to, like I said, you can ask it, how sure are you about it? And you can have long conversations with it about any of these facts. And it's a pretty solid way to suss out what is true from what is false. So I think there's a lot of potential there for, if you can automate that process or do something like that, maybe potentially reducing the hallucinations. But understanding why they occur, as I say, I mean, that's part of the point of our paper, is it's a statistical predictor initially. And so why it's occurring is, kind of, maybe not that complicated. I do, can I just make a comment also about a question we had before? So I'm just looking at the system card because I'm not really allowed to speak outside of what we publish. So let me just, so in the system card, yeah, I believe that it says that we have received reports, anecdotal reports of the language model hallucinating O1 more. And, we're very interested in learning more about that. If anyone has any analysis they want to share, or even cases, we would really like to know more, because obviously that's one of the big areas we want to improve in. Any more questions?
Yeah, so there is one question from Mitchell about, so he's curious if how far we want to push this chatbot abstraction when it comes to LLMs, and whether LLMs should each LLM should have like a predefined use case for which it was trained, and then should only be used for that purpose. I mean, here we have this one model that's being used to generate poetry, where it kind of has to create new text, and also to answer factual questions, right? Where it should be just either, yes, I know this fact, this is the answer, or I don't know, right? And so should this distinction be made? Is that the way to go forward, or is there something else?
Very interesting point. I like that idea a lot. As you're saying, if you have a bunch of special case tools, you don't think of the chatbot as and you don't anthropomorphize it and think of it as an agent that can answer any kind of question, but you just think of it as a one-off. And if you try to define narrow tools, people build a lot of really great tools for these things. And even the references, there's some companies, I think Elicit is an example of one, where they try to nail that problem specifically. And so when people pick a narrow domain and use language models in these domains, and then you have these tools, I think that's a great way to address the hallucination problem, because then the system designers can try to perfect that one domain and reduce hallucination. So that's a great point.
Perfect. We have time for one more question. And Christina, you have raised your hand. Would you like to unmute and ask?
Sure. Dan Brown and I were chatting a bit in the background. So I think I'm coming at this from the point of view of an educator, and I'm working with my students. So my class is very case-based. I'm in strategy. I've got business students, and they're just using these tools with no guardrails, no clue what they're doing. It's just like throwing spaghetti at the wall and seeing what's sticking. And I'm encouraging them to stop and ask questions about what they're doing, what they're seeing. And I think this point of this being trained on Reddit, it really stuck with me, because I'm watching my student essays starting to sound really inconsiderate, non-compassionate, bold, ballsy, no nuance, stuff. And I'm wondering where it's coming from. And I think some of it's coming from interacting with ChatGPT and getting the sense that this is how we should talk, and that's just fine. And I'm just sort of struggling with what kind of tools can we bring to bear against this, besides just trying to remind them, or or some checks or some processes they can follow, because really it's like the Wild West in my classroom.
Yeah, that's a great question. As I said, I can't comment on the specific training data that we're using, but it is carefully selected, and we do not, it's curated. And so, we don't just take offensive text that's been written in, various ways and throw it into the training set. My personal experience with ChatGPT is that it's relatively polite in the way that it writes. But I'm sorry to hear that the students are writing that way, and that you feel that that's coming from their interactions with ChatGPT. I don't have, that's a really good question. I agree that it's definitely a coevolution. This is, how these models come to be, how they're adjusted, how they're used, and how they influence people is very important.
It's not rude behavior, but I'm seeing this sort of almost like social dynamic, and I experience it as a speaker too, where people want a confident, unnuanced response so desperately. And I'm seeing this real shift quite recently that's just, it's like on steroids, and it deeply concerns me in terms of, like, what should my guidance be as an educator when I see this in my classroom?
You're saying people are mimicking the confident responses.
Even when they're not.
Right. Well, people might maybe do the same. Yeah, in the same way that if you had a child, maybe put them in this room full of professors and they hear everyone talking with great confidence, and then they come out and they, yeah, that's a problem.
I just gave a talk on Friday at Rotman where I said, look, I am not going to predict the future. And then Q&A happened, and one question after another was, please predict the future. And it was just like
Yeah.
what part of this did you not understand?
Do you have any strategies that you use with the students to kind of keep them from being overconfident?
My go-to is always reflection. Is to say stop and ask, why are you proceeding this way? What are you getting out of this? What's the trade-off? I feel like I'm this one trick pony. It's like, what's the trade-off here? And in a few places you mentioned trade-offs, and I wonder if some sense of like making the trade-off transparent. Where people recognize you could, get a certain level of accuracy at the cost of, more hallucination or whatever. And then people could really understand there's no one right approach, but we're constantly on this frontier of trade-offs, and we're just picking a place. And maybe that's not everybody's favorite place to be.
Right. But you're saying this is that's a good point. You're saying this is a more recent phenomenon. I mean, there's the classic examples where you ask people, why is it colder in the summer than the winter? And everyone with great confidence gives the wrong answer and says it's because we're further from the sun. So that's always been a problem. But I'm interested to hear that you are experiencing that, like you feel like there's a big change very recently.
There's been a huge change in writing tonality and in the classroom dynamic as well. And it's really, I know a lot of people want to chalk this up to COVID and remote learning, but I think it runs deeper than that.
I see. Interesting. Thank you. Great point.
All right, thank you, Christina. Thanks, Adam. I think we may have time for just like squeezing in one very short question. So Luca, if you don't mind, I can just read out the question on behalf of you to just in the interest of time. So given the vast range of potential text inputs and the combinatorial complexity of language, how can we effectively actually put in these mitigation strategies to prevent prompt injection in AI systems while still ensuring performance and accuracy? And doesn't the system card actually make it seem like we are laying the rails while the train is still moving?
Huh. Interesting. It's a complicated question. I think I'm actually going to pass on it. I mean, it's not directly related to hallucinations. I will say that there is a combinatorial complexity of language. There's infinitely many ways to ask about the same question. But the language models do have deeper representations. And so I don't think that the fact that there's infinitely many ways to represent the same question is inherently a problem. The language models seem to understand that many of them represent the same thing.
All right, perfect. Well, thank you so much, Adam, for such an engaging and thought-provoking presentation, as well as the discussion. I think we really kind of all enjoyed it. And thanks to everyone in the audience for being with us today. This concludes our today's seminar. Please join us next week, Wednesday, October the 2nd, as we are very excited to welcome preeminent computer scientist Cynthia Dwork from Harvard University for a talk on prediction, fairness, and complexity theory.